At 4:37 in the morning, local time, a Los Angeles-class attack submarine was on the hunt. It was positioned 20 miles south of Sri Lanka, deep beneath the surface of the Indian Ocean, and its mission was to find and destroy enemy ships. Up above, on the surface, an Iranian warship named the Iris Dina was doing exactly the opposite. The Dina, one of the last remaining combat ships in the Iranian surface fleet, was actively searching for submarines. The ship was moving back and forth in a zigzag pattern at a speed of 15 knots, and its crew was using active sonar, which means they were sending out loud pings of sound into the water, hoping those sound waves would bounce off a hidden submarine and reveal its location. The men on the Dina had no idea that they were the ones being hunted. They were searching for a predator that was already watching them from the depths. Soon, the American submarine's captain would receive an order from CENTCOM, the United States Central Command, an order that no American submarine commander had been given since the days of World War II. But before that order could be carried out, the submarine first had to get into the perfect firing position, and that was going to be incredibly difficult. The Dina was doing everything it could to make itself a hard target to hit. The ship's hull sonar was hammering the ocean with active pings, sending out bursts of sound and listening for any echoes that might come back from a submarine's steel hull. At the same time, its ASR 3D radar was sweeping in a full circle around the ship, watching the surface of the water for anything unusual, like a periscope or a communications mast poking up. But the most challenging part for the American submarine was the way the Dina was steering. Every 3 to 5 minutes, the Iranian captain would order a random change in direction. The ship would suddenly turn left or right, zigging and zagging without any predictable pattern. This was a clever tactic, and it was designed to exploit a basic weakness in how submarines track their targets. When a submarine is hunting a surface ship, it usually relies on passive sonar. Passive sonar doesn't send out any sound. Instead, it just listens. The submarine's sonar operators can hear the noise made by the ship's engines and propellers, and they can tell what direction that noise is coming from. They know the bearing, which is the compass direction of the ship, but passive sonar alone cannot tell them the distance. They don't know if the ship is close by or far away. They only know which way to point. To figure out the range, the speed, and the exact course of the target, the submarine's fire control technician has to do something called target motion analysis. The technician watches a display that shows the bearing of the target over time. As the submarine and the ship both move, that bearing line slowly creeps across the screen, changing by a degree here and a degree there. By carefully measuring how that bearing changes over many minutes, and by feeding those measurements into complex mathematical algorithms, the technician can eventually triangulate the target's position. He can start to calculate how far away the ship is, how fast it's going, and in what direction. On the display, a green line represents the computer's best guess, and as more data comes in, that line slowly converges toward a solid firing solution. It is like watching a blurry photograph slowly come into sharp focus. The picture gets clearer and clearer until the technician knows exactly where to aim the torpedo. But the Iranian captain on the Dina was making this almost impossible. Every time the American technician's green line started to get close to a solid solution, the Dina would zig. The ship would suddenly change course, and the green line on the display would scatter. All that careful work, all those minutes of tracking, would be wiped out in an instant. The technician would have to start over from the beginning. He would watch the new bearing, form a new hypothesis about the ship's movement, and start the slow process of watching the green line converge all over again. The captain was shaking the camera every single time the picture was about to come into focus, and he was doing it with a rhythm that kept the American crew constantly off balance. This skill was not an accident. The Iranian captain had spent 2 weeks taking part in a huge multinational naval exercise called Milan 2026. These exercises were held with the Indian Navy and included ships and submarines from many different countries. During those 2 weeks, the captain had practiced exactly these kinds of anti-submarine maneuvers over and over again. He had drilled his crew on how to make their ship a difficult target. The Americans had been watching those exercises, of course. They had observed the tactics and taken notes. Now, one of their own submarines was trailing the Dina like a patient ghost, and the Iranian captain's training at Milan was the only card he had left to play. It was his one advantage in a deadly game of cat and mouse. But as challenging as the zigzagging was for the submarine's fire control team, it was not the thing that worried the Iranian crew the most. What really worried them was sitting right on the Dina's own flight deck, at the back of the ship. It was an SH-3 Sea King helicopter, and this was no ordinary helicopter. It was an anti-submarine warfare aircraft, and its only job was to find and kill submarines. The Sea King carried a special piece of equipment called a dipping sonar. This was a low-frequency sonar system designed to do one thing better than anything else, which was to find submarines in places where a ship's hull sonar could not reach. The Dina's hull sonar was mounted on the bottom of the ship. It sent its pings out from the surface, and those sound waves had to travel down through the water to reach the depths where a submarine might be hiding. But the dipping sonar on the helicopter worked completely differently. The Sea King could fly out to a spot, hover low over the water, and lower a transducer on a long cable straight down through the water column. It could drop that microphone right through the thermal layer, that natural boundary in the ocean where warm surface water meets colder deep water, and it could send its ping from the same acoustic environment where the submarine was hiding. The thermal layer, which normally acts like a shield to hide the submarine by bending sound waves away, would stop working the instant that transducer splashed down below it. A single competent helicopter crew, working with a dipping sonar, could leapfrog across the ocean, moving from one hover spot to another, and sanitize an entire search box. They could clear a huge area of ocean of any hiding submarines much faster than a surface ship could ever hope to cover the same ground. A full day of searching for a ship could be done by a helicopter in just a few hours. 400 feet down, deep beneath the surface, the American submarine's sonar team was listening intently. They were straining their ears to hear any sign of that helicopter through all the ambient noise of the ocean. They heard nothing so far, and that was good. But the absence of sound did not guarantee anything. Sound behaves strangely in the ocean, especially when there is a thermocline. The ambient noise from the surface, from dozens of merchant ships passing by, from the crackling sounds of snapping shrimp colonies living on the continental shelf, all of that noise was being bent and scattered by the thermal layer. Just because the sonar team could not hear the helicopter did not mean the helicopter was not there. If the Sea King launched while the submarine was still trying to close the range to the Dina, the Americans would have only two choices. They could shoot immediately, firing their torpedo before the helicopter could establish a proper search pattern and find them. Or they could go deep, diving below the layer and trying to hide. But that would mean losing their firing window on the Dina entirely. There was no middle ground. It was either shoot now or hide and let the target get away. For the moment, the thermocline was doing its job. It was protecting the submarine. The thermocline is a boundary in the ocean where the warm surface water meets the colder deep water. This boundary bends sound waves in the same way that a prism bends light. When the Dina's hull sonar sent out its active pings, those sound waves traveled down through the water until they hit the thermocline. At that boundary, the sound waves were refracted upward. They bent away from the submarine and curved back toward the surface. The Iranian sonar operators on the Dina watched their screens and saw nothing but empty ocean. But the thermocline is not a solid wall. It is more like a lens, and lenses have quirks. The American sonar chief knew this all too well. He watched one of those quirks on his display, and he knew it threatened to expose them. Sound traveling through deep water does not just disappear. It behaves in complicated ways. Sometimes sound waves bend downward, traveling deep into the ocean until they strike a density boundary, and then they arc back up toward the surface. These arcs happen at roughly 30-mile intervals. They are called convergent zones. In these zones, a sound ping that should have faded away to nothing 50 miles ago arrives at a sonar receiver as loud and clear as if it were right next door. If the Dene happened to send out a ping at just the right angle, and if that ping caught one of these arcs at just the right spot, the Iranian sonar operator would suddenly paint a contact on his screen. He would see an echo coming from a spot where there should be nothing, and that spot would be exactly where the submarine was hiding. It would be a stroke of bad luck, a piece of unlucky geometry that could give away the submarine's position in an instant. And there was another problem. The thermal layer was thinning. The American technicians had been dropping small devices called expendable bathythermographs into the water. These instruments measure the temperature of the ocean at different depths. Every time they dropped one, the readings came back a little warmer than the last. The warm surface water was slowly mixing with the cold deep water, and the boundary between them was weakening. The sonar chief studied the data and made a grim estimate. He figured they had about 6 to 8 hours before the thermal layer degraded past the point where it could reliably conceal them from the Dina's sonar. The Dina was streaming roughly parallel to the Sri Lankan coast at 15 knots. At its current course and speed, the ship would cross the 12-mile territorial limit in about 40 minutes. Once it entered those waters, international law would protect it. The submarine could not legally fire a torpedo at a ship inside another country's territorial waters. That was a second clock ticking. And on the aft flight deck of the Dina, the Sea King helicopter sat fueled, armed, and ready to launch. It was only one captain's order away from taking off and turning the submarine's hiding spot into an open auditorium. All three were ticking simultaneously. So at 4:41 in the morning, with the thermal layer thinning, with the helicopter just a coin flip away from launching, and with the fire control team struggling to track a zigzagging target through an ocean full of noise, the submarine needed something it could not get from down in the deep. It needed the execute authorization from CENTCOM. That order could not reach them at their operating depth. Submarines use something called ELF radio, which stands for extremely low frequency. These are the only radio signals that can penetrate deep into the ocean and reach a submerged submarine. But ELF radio carries almost no information. It has almost zero bandwidth. The only thing it can really say is a simple signal that means, come to the surface and check for messages. It is enough to tell the submarine to come shallow, but it is not enough to transmit a complex targeting authorization. To get the actual order, the submarine had to rise to periscope depth. That meant leaving the safety of the thermal layer. It meant coming up into the water column where the Dina's hull sonar worked best. It meant pushing a communications mast above the surface, sticking it up into the air where the Dina's ASR 3D radar could potentially see it. The radar was scanning for exactly that kind of small, transient contact that a periscope mast creates. But the American crew had a trick. There was a South Korean LNG tanker nearby. It was a massive ship, 200,000 tons of liquefied natural gas, and it was plowing through the ocean about 5 miles to the southeast. That tanker was huge, and it was throwing a massive radar return onto every radar screen within 50 miles. The submarine's navigator had been tracking that tanker for the past hour. He had been waiting for the geometry to align perfectly. The plan was simple, but brilliant. If the submarine came up to periscope depth along the exact line of bearing that ran between the tanker and the Dina, then the submarine's small mast would sit directly in the tanker's radar shadow. It would be hidden behind the massive radar return of the big ship. When the Dina's radar operator saw a faint blip on that bearing, he would check it against the known position of the tanker. He would see that big ship sitting right behind it, and he would dismiss the small blip as a ghost, a side lobe reflection caused by the tanker's enormous steel hull. He would think it was just radar clutter, not a submarine. It was a perfect deception. At 4:48, the geometry finally lined up. The officer of the deck gave the order to ascend. The submarine rose up through the thermocline. As it climbed, the flow noise of water rushing over the hull began to build. The thermal shield that had kept them hidden peeled away. The sonar picture degraded as ambient noise from the surface flooded in. 3 days of careful hiding, 3 days of invisibility, were traded for just a few seconds with a mast above the water. The communications mast broke the surface. The satellite link locked on. Message traffic streamed down. The authorization was confirmed. The submarine immediately dove back down beneath the layer. The thermocline closed over them like a door shutting, and they were hidden again. Back on the fire control displays, the Dina's bearing continued to tick eastward. The ship was still zigzagging, still pinging, but now the geography was squeezing the submarine. At 4:51, the Dina's course was tracking parallel to the Sri Lankan coast, about 20 miles offshore. The 12-mile territorial limit was only 8 miles to the north. If the Iranian captain got spooked, if he suspected he was being hunted, he might turn toward shore. He might run for those protected waters. International law would make those waters untouchable. The Iranian crew would rather be interned by Sri Lankan authorities in Colombo than be torpedoed by something they could not see. Every minute the submarine waited, the Dina steamed closer to that line. At the end of the cable was a sensor that was the submarine's sharpest ear. It was the best tool they had for listening to the ocean. But the moment a torpedo launched, if the submarine needed to maneuver hard to avoid counterattack, that array would become a leash. It could not be retrieved quickly. Aggressive turns risked tangling the cable around the propeller or even snapping it clean off. The boat's best sensor was about to become its biggest problem at the worst possible moment. At 4:53, the fire control team finally locked the solution. They had solved the math problem. They knew exactly where the Dina was, exactly how fast it was going, and exactly where it would be in a few minutes. The weapons officer programmed the Mark 48 ADCAP torpedo that was sitting in tube number 1. The captain gave the order. The torpedo tube flooded. Seawater rushed in to equalize the pressure inside the tube with the pressure outside the submarine. That rush of water created a sharp acoustic transient, a sudden sound that a trained sonar operator on the Dina would recognize instantly, the way a parent recognizes their own child crying in a crowded room. The submarine crew was betting everything on the thermocline, on the noise from all the shipping in the area, on the millions of snapping shrimp crackling on the continental shelf. They were betting that all that noise would drown out the sound of their torpedo tube flooding at the worst possible moment. The Mark 48 dropped from the tube. It was 21 inches in diameter and weighed 3,500 pounds. It was a guided weapon, and it ran on something called Auto Fuel 2. This was a special monopropellant that carried its own oxidizer. That meant the torpedo needed no air intake to burn its fuel. It produced no exhaust bubbles rising to the surface to betray where the shot had come from. The engine drove a pump jet propulsor instead of a traditional screw propeller. That meant no cavitation trail, no telltale line of bubbles on the surface. The only signature the torpedo gave off was acoustic, the hum of its engine. And that hum was swallowed up by the ambient roar of one of the busiest shipping lanes in the world. Behind the weapon, a thin wire spooled out. It was hair-thin, connecting the torpedo to the fire control technician's console. Through that wire, the operator could steer the weapon. He could guide it around obstacles, adjust for sudden maneuvers by the target, and even override the torpedo's own seeker if the enemy tried to fool it with countermeasures. The trade-off was that the submarine was now chained in place. It had to hold its course and depth perfectly. It could not maneuver aggressively. It could not run away. It could not do anything that might stress or snap that fragile wire. If the wire broke, the torpedo would go autonomous. It would rely on its own brain to find the target. At its transit speed, the Mark 48 was essentially deaf. The flow noise of water rushing over its own sonar dome drowned out the ocean completely. The fire control technician had to steer it blind, using only the guidance data scrolling across his display. He was threading a weapon moving at 55 knots through a busy shipping lane, all while sitting deep beneath the surface. The distance to the Dina was 7 nautical miles and shrinking. If the Iranian ship made an unexpected turn toward those Sri Lankan territorial waters to the north, the technician would have only seconds to react. He would have to bend the torpedo's track, using that hair-thin wire, to adjust the weapon's course while the torpedo itself could not see where it was going. At 5 miles, the Dina zigzagged again. The bearing shifted on the fire control display. The technician calmly adjusted the torpedo's gyro course through the wire, bending the intercept geometry to match the new heading. Every correction ate up more of the wire. Every degree of turn lowered the margin between a perfectly guided weapon and an expensive piece of junk that would miss its target. At 4 miles, the submarine crossed over the edge of the continental shelf off Galle, Sri Lanka. The shelf dropped away into deep Indian Ocean water. This depth gradient squeezed the torpedo's performance envelope from every direction. If the torpedo went too shallow, it might broach the surface and be seen. If it went too deep, its runtime would stretch out, giving the Dana extra seconds to turn or escape. The three-dimensional box that the navigator had been managing was shrinking with every mile. At 3 miles, the Dana pinged again. That sonar pulse radiated outward through the water and passed right over the torpedo. It was like a searchlight sweeping past a burglar hiding in the dark. The Mark 48 was small enough, and it was moving fast enough, that if there was any return at all, it would probably look like biologics on the Dana's sonar screen. At 2 miles, the Mark 48 slowed down. The flow noise dropped away, and the torpedo woke up. Its onboard sonar, a sophisticated 2D phased array seeker that could be steered electronically, started painting the water ahead. It began sending out active pings at high frequency. A 1,500-ton frigate pushing 15 knots of displaced water through the Indian Ocean is not a subtle target. The seeker locked onto the Dana almost instantly. Terminal acquisition. The weapon accelerated for the final run. Now the Dana heard it. Somewhere on that ship, a sonar operator caught the sound that every sailor in every navy prays he never hears. It was active pinging, closing fast, and the bearing was consistent. Bearing consistent meant it was not passing by. It was coming straight for them. He hit the alarm. The bridge heard it. The captain heard it. 15 seconds separated that moment from impact. The Dana carried acoustic decoys, expendable noisemakers designed to seduce torpedo seekers away from the real hull. To use them, the crew had to recognize the threat, authorize countermeasures, and physically throw them over the side. That sequence, for even a well-trained crew on a good day, takes longer than 15 seconds. A hard turn, trying to dodge, would not help either. A 1,500-ton frigate at 15 knots needs hundreds of meters to come about. It did not have hundreds of meters. The triple 324mm torpedo launchers on the aft deck could reach out 30 kilometers. But to fire them, the crew needed a bearing on the submarine that was attacking them. And that submarine was still sitting 400 feet down, beneath the thermocline, invisible, untouchable, and patient. The Dana could hear the torpedo arriving, and it had no idea where the torpedo had come from. Even if the decoys had somehow made it into the water, even if they had deployed in time, the fire control technician on the submarine was ready. He was sitting at his console, watching through the wire, ready to override the torpedo's brain and steer it manually past the noisemakers and onto the real target. The Mark 48 did not hit the hull. It passed directly beneath the keel of the ship and detonated. The warhead had a magnetic influence fuse. It detected the Dana's steel hull passing overhead, and it fired at the optimal point, directly beneath the keel. The keel is the structural spine of a ship. The explosion created a massive gas bubble that expanded upward with incredible force. That bubble lifted the Dana's entire 1,500-ton stern clean out of the Indian Ocean. Then the bubble collapsed. The stern fell back down. The keel snapped. The bow of the ship pitched skyward, silhouetted against the pre-dawn sky, while the aft section dragged everything down. 94 meters of Iranian naval engineering folded in half and slipped beneath the Indian Ocean. At 5:08 in the morning, local time, the distress call went out. By the time Sri Lankan rescue boats reached the coordinates, there was nothing left but oil slicks, debris, and life rafts drifting in the pre-dawn current. The American submarine slipped back down below the thermocline. No periscope was raised, no transmissions were sent, no trace was left behind. The towed array kept streaming behind the boat as though the last 40 minutes had been just another drill. The reactor hummed quietly. The ocean closed over the space where the submarine had been, like it was never even there.